In this video, we'll show you how to use calculus to sketch the graph of a polynomial function. So we're going to begin by recording the domain of this function. Domain is all real numbers because polynomials don't have any restrictions. In step 2, we will try to identify the intercepts, and we can start with f0. At 0, the function is equal to 1. And then we can try and find the x-intercepts. Since the function is given to us in factored form, we easily find the x-intercepts. They are x equals 1 and x equals -1. In step 3, I'm going to construct the sign chart for the function itself. So I'm going to use the x-intercepts and the multiplicity at each intercept to figure out the signs for the function. On the right side, since the leading coefficient is positive, the function itself will be positive. At 1, multiplicity is even, so the function does not change the sign, and at -1 it becomes negative. So at this point we kind of have an idea of what the graph of this polynomial function look like. Also, by looking at the leading coefficient, we know that the graph's going to look like x cubed, so it's going to be opening up on the right side and opening down on the left side. In step 4, we would like to find the derivative of the function, and I'm going to use the standard form. So derivative of this function is -1 minus 2x plus 3x squared, and I'm going to write it like this, and then I'm going to try to factor it. So we have 3x squared minus 3x plus x minus 1, and 3x plus 1 times x minus 1 will be the derivative of this function in factored form. So that means if we were to analyze the derivative of this function by constructing the sign chart, for the derivative, we would get the following. The critical points are at 1 and -1/3. And since the multiplicity of each factor is odd and the leading coefficient is positive, we know that the function will be positive on the right, and then it will change the sign at every point, and this has the following effect on the graph of the function. It's increasing on the interval from -infinity to -1/3, decreasing from -1/3 to 1, and then increasing from 1 to infinity. That means we have at -1/3 a local max, at 1 we have local minimum. And to improve the accuracy of the graph, we can find f of -3 and f of 1. F of 1 is 0. This is actually the x-intercept of the function, and at -1/3 we have -4/3, so 16/9 times 2/3, so it's 32/27, so it's about 1. Now in the next step we find the second derivative, so we can perform the analysis of the second derivative. I'm going to differentiate the first derivative, and the derivative is equal to 6x minus 2. So that means the sign chart for the second derivative will look like this. So we have a 0 at 1/3. On the right side it is positive, on the left side it is negative. That means the original function will be concave down on the left and concave up on the right. And now we can piece it all together and sketch the graph of this polynomial function. So to graph this function, I'm going to start with the x-intercepts. which are at -1 and 1. I know my function will be increasing to the right of 1 and to the left of -1/3. So here's the general shape of this function. At 0, the function is 1, so it bounces at 1, so it looks something like this, right? So it bounces at 1 and it passes through -1. So now one thing we don't know from this picture, from this little sketch, is that where exactly the function turns around. And for that we're going to use the first derivative analysis, which says that the function actually turns around at -1/3. So it obtains its maximum at -1/3, and the maximum is 32/27. So at -1/3, the function gets barely above 1. So this is my local max. At 1, on the other hand, we have local min. Now, another thing that we learned from the analysis of the second derivative is that at 1/3 we have the inflection point. And what is the value of the function at 1/3? We can just plug it in to find out. So it's 4/9 times 4/3, so it's 16/27. So it's about half, slightly greater than half. So at 1/3 the function is at 1/2. So we have a inflection point here, and now we can piece it all together. So function comes from -infinity, concave down, goes through -1, reaches maximum at -1/3, turns around, passes through the y-axis at 1, goes to point 1/3, 16/27, where it changes its concavity. So it's from concave down, now it becomes concave up, goes to 1, where it bounces off the x-axis and goes back to infinity. So this is how we use calculus to sketch the graph of a polynomial function.